minus 2, which is the x-coordinate of the left endpoint of the rectangle. So the difference between these two x-coordinates is going to be the length of this rectangle. And so, since the length of that rectangle is always 4 minus y squared minus y minus 2, I can just take that expression, multiply by the thickness of the rectangle, and then integrate up the y-axis from negative 3 to 2. And this just turns out to be much easier because on the one hand, for one reason it's one integral, on the other hand it's all polynomial. So, and hopefully what you were supposed to do for homework, sorry you had to do this because it was like, it takes like 15 minutes, do this integral, did you guys get the same number? If so, then you like learned your lesson, which is like sideways rectangles are sometimes great. Okay, Shay, are we good? Yeah. Okay, that was 13. Going a lot faster. Let's do number 69. How tricky? Yo. Yes. Number 69 said that there's this function, f of x equals 1 over x squared plus 1, and there's a point 1 comma 1/2. I like this problem because it's a little bit of everything. Did you do your homework? Juniors! I'm sick of juniors. Guys have bad study habits, only except for Junie. You and all. Jimmy, did you do your homework? All of it? Take it back. Maybe it's just you. All right. Yoni, you have to do your homework. This is hard. Okay. 1 over x squared plus 1 and the point 1 comma 1/2. So here's what you had to do. Set up and evaluate the integral that gives the area of the region bounded by the graph of the function and the tangent line to the graph at the given point. All right, so there's no way to do this without drawing a really, really good picture. If your picture's bad, you're probably going to have no idea what the hell's going on. So what is the curve 1 over x squared plus 1? What does it look like? It's like a parabola, moved up 1 and like reciprocated, right? So you get that weird like jump jump. It's like this, we've seen this before back in the parametric unit. It's like the Witch of Maria Agnesi.
Yeah.
Yeah. Something like that. And according to the book, if I plug in 1, I'm going to get 1/2. Is that true? Yeah. Okay. So that is the point 1 comma 1/2. And I'm supposed to find the area of the region bounded by the curve and the tangent line to the curve at 1 comma 1/2. All right, well, in order to do that, I need to find out what the tangent line is. So I need to take this function and differentiate it. So this function is x squared plus 1 to the negative 1. So what's the derivative? Is negative x squared plus 1 to the negative 2 back inside 2x. So the derivative of this function is negative 2x over x squared plus 1 squared. But what I really want to know is what's the derivative at 1? If I plug in 1, I get, what do I get? Someone did this problem?
Negative 1/2.
Negative 1/2. Okay. So that means that the slope of the tangent line to the curve here is negative 1/2. And if the slope is negative 1/2, well, I know it's going to touch here. Where else is it going to touch? I guess I need to figure that out, right? So what is the equation of this tangent line? Well, the equation of this tangent line is going to be y minus 1/2 equals negative 1/2 x minus 1. Just using point slope form. And then rewriting this to make it a little bit prettier, it's negative 1/2 x, let's see, plus 1/2, so plus 1. Okay, so that's the equation of the tangent line to the curve at 1 comma 1/2. Where does this curve intersect this function? Well, it's pretty clear that it's going to intersect at 0, 1, right? This curve goes through 0, 1, and this line also goes through 0, 1. So if I'm going to draw this tangent line properly, the tangent line looks kind of like that. Okay, so after all of this work was really actually just to set up the problem. And the problem is, the setup to the problem is, I'm going to like redraw my function now and then I kind of, oh, what's up? The entire problem is find the area of this tiny region. The gap between the function and the tangent line to the function. And now that I've done that, I can draw a representative rectangle, and so the area of this region is going to be the integral from 0 to 1 of function minus line. So it's going to be plus 1/2 x minus 1. And now that's not such a hard integral to actually do, right? Because that's just like arctan x, and then that's like x squared over 4, and then that's minus x, and evaluated at 1 and 0. So it's like, what is it, pi over 4 plus 1/4 minus 1? So you get pi over 4 minus 3/4 is your final answer?
Yeah.
Which is a tiny number, because pi is like a tiny bit more than 3. All right, how are you feeling on this? Good? All right, let's do just like a couple more problems. 75 I thought was kind of cool, even though it's not hard. You have to explain to someone like, what is the whole point of like this whole finding the area between two curves thing again? 75 says a college graduate has 2 job offers. The starting salary for each is $32,000. Okay, so excellent job offer, $32,000. The salary increase for each offer is shown in the figure. From a strictly monetary viewpoint, which is the better offer? Okay, well, sort of like duh, but on the other hand, all right, so this is salary, and the units for salary are, dollars per year. In other words, even though you probably don't think of it, you probably think of salary as just a number. In fact, salary is like a rate of change. But it's sort of the rate of change of the amount of money that you've earned over your lifetime. It's the amount of money you're earning per year. And now if we look at this over years, on the one hand, it seems that regardless of which offer, eventually you're going to end up at the same place, right? So this is offer 1, and this is offer 2. Alright, well, I guess you would be just kind of stupid to choose offer 1 over offer 2. But if you were kind of, but you'd be surprised. Both of these offers have the employee by the end of year 8 making the same amount of money. This comes up a lot actually in like contract negotiations. For example, in my job here in Montgomery County, when they negotiate the contract, there's this particular. Well, should I finish this problem first? Here, let's finish this problem. So both of them have the guy making $32,000, and both of them have the guy making whatever $54,000 by the time he gets to year 8. But over all those years, by accepting offer 2, you're making more money, right? And if you actually start drawing rectangles, like for example, let's just go to like year 3, right? If I draw the rectangle. Then what is the meaning of that rectangle? The rectangle drawn on the interval 3, 4.
How much more money he earns that year.
How much more money he earns that year by being paid via the offer 2 plan versus the offer 1 plan. And then I can just draw a new rectangle between year 4 and 5. And the new rectangle between year 4 and 5 is the difference in how much more money. So the area between these two curves is what? The total area between these two curves is? It's like the total accumulative amount of money earned more by accepting offer 2 versus offer. This is 73, yeah, that's what I said. Oops. Because I wrote the wrong thing. Yeah, and this comes up like in our salary for teachers. They used to do this thing where it took until you got to year 25 before your salary like leveled off. So you would get to you'd start like at year 1 making like some amount of money, and then it would kind of like get bigger and bigger and bigger. And then when you got to year 25, then you wouldn't get any more raises forever. And then they realized, and this is like a little bit subtle. Oftentimes, if you're smart, you can like trick people who are stupid. That's like the reason for learning. So they restructured things earlier, and they said, okay, well now your cap salary is still going to be the same, but now we're going to get you there in 20 years instead of 25 years. And so now it looked kind of like this, and then. So these were the two. So we negotiated basically the blue salary over the black one, and that's just like way better, right? Because the area between these two curves represents all that area, is like the total amount of money one earns over their career more by following the blue path as opposed to the black path. So, I don't know, that's like a thing that comes up a lot in these kinds of discussions. Okay. Do we even have time? Let's do one more problem. 75, 93, or 94? 94, you might groan a little bit upon hearing how to do 94 because, well anyway, I'll just show you. 94 is an awesome problem which says, find the area inside an ellipse. So we talked about ellipses last semester. So this is x squared over a squared plus y squared over b squared equals 1. Can you, yeah, good. So, and the ellipse itself looks like this, and I think there's even like a picture in the book and stuff. Goal, find the area inside an ellipse. Well, guys, on the one hand, this is kind of just like obvious, right? Because what is an ellipse after all but a stretched out circle? The area of a unit circle is pi. And so if you take a circle with radius 1, don't you just feel that the answer should be like, well, okay, take a circle with radius 1. Stretch out that circle so that it has radius 5. What should the area of the new circle be? Well, you're stretching it out by 5 in the x direction, but also 5 in the y direction. So when you stretch it out by 5 in the x direction, the area becomes 5 times as much. And when you stretch it out by 5 in the y direction, it becomes 5 times as much. That's why the area of a circle is pi r squared, because you're like stretching out the radius in two directions. But now I'm stretching out by a factor of a in the x direction and by a factor of b in the y direction. So don't we just kind of like know that the answer is pi ab? Okay, I feel like we just know that. Okay, how do we prove this? Permit me to just find the area of a quarter of the ellipse and then just multiply by 4. So I say that the area is going to be 4 times the integral from 0 to a of, well, I guess I need to figure out how tall this function is. So in order to figure out how tall this function is, I need an expression that will return for an arbitrary x value, like what the y value is. Okay, but I've done stuff like this before, right? I just need to solve for y. So you get like y squared over b squared equals 1 minus x squared over a squared. Seen all this kind of crap before?
Yeah.
And then like get a common denominator over here, multiply by b. And so we end up with is y squared equals a squared over b squared times a squared minus x squared. So finally, y is a over b root a squared minus x squared. Did I mess up? Oh yeah, I did mess up. That should be b squared. That should be a squared. Thank you. Okay, so that's really it. The thing, I'm adding up a bunch of rectangles, each of whose heights is b over a root a squared minus x squared, and the width is just dx. And now I just need to do this integral. Well, this is 4, I can take out b over a, so that's an integral from 0 to a of root a squared minus x squared dx. So did some of you get this far? And then you were like, how do I do this? How do we do this?
That's a circle.
Yeah. Yeah, so D.D. Shetty says, dude, it's just a circle.
Couldn't you just said that about the entire ellipse?
Kind of, yeah. So that's why I said you might groan now, right? I mean, the way I think that the book intends for you to do this at this point is just to be like, yo, that's a circle. In other words, don't forget, just because you learned the fundamental theorem of calculus, don't forget that we did integrals like this even prior to learning the fundamental theorem of calculus, right? This is just a circle, or in fact, it's a quarter circle. And so my way of solving this problem is just to say, yo, this is just, Yeah, it's just pi a squared over 4, and then you just get the answer. Alright, now, Lathrop says stupid. Others of you might feel like we're cheating or something. I am sympathetic. So I guess the follow-up question would be, is it possible to prove the formula for the area of a circle by actually like doing this interval? Is that possible?
Oh,
And the answer is yes. So if you would like a challenge, please attempt to do this interval with like integration skills. However, it is something which I wouldn't be shocked, well I would be pretty damn impressed, but not shocked if you could figure this out. It involves advanced techniques, which I have not taught you, and which you're going to learn next year in Analysis 1B, but you could just like ask some junior and they could tell you how, or you could maybe just try to figure it out on your own or look on the internet. It wouldn't be any big mystery, but it's hard. But it's doable. Okay, but for now, this is good. All right, can I have this homework? And then we're going to learn a new thing.
All of it?
Yeah, I guess there's two things, right? 366 and
Let's do last class.
Oh, yeah.
yeah. We still gotta do that part.
did I not collect the homework on Friday?
Yeah, you did.
Oh, I mean,
You did not.
Like bookwork, like 351 or something like that, right?
329.
329.
Yeah.
Right. This was the class where I posted the homework late and you guys were like crying about it, so I just didn't collect the homework. Yeah. So can I just have it all like in one big? We're just gonna do it in one big stapled, one big. So it's like 329. It's like page 329, 4 problems. Page 359, like 10 problems. Page 366, like 5 problems, which I thought were hard. And page 454, all together in a big staple. Let's put it over there on that other staple. Thank you.
Staple it all together.
Yeah, staple it all together. Just the bookwork. Hold on to the packets. They will be. They will be collected on Friday. And then we're going to do something really awesome. Starting now. If you now have 49 I guess that's enough.
Yes.
We're going to do a sort of fast version. Yeah, so Liam, can you put the camera over here? We're trying to give everyone one of those.
Guys, try and staple Garrett.
Oh. Don't staple Garrett. I have one. Yeah. Johnny, can you write the board? What's up?
I have some of it.
Is this on?
I think so.
Yeah, the camera is running through our.
Should I pose in front of it?
Yeah, stop. It's really not a cool plus one. Okay, so I think the pulse in the eighth row is.
Alright, stop.
Yeah.
Class, we're about to do something pretty fun and great. I would like to talk about volume. Alright. Well, that's just like area, but like 3-dimensional or something, right? Recall the area problem. The area problem was find the area of stuff. Brittany, how did we solve the area problem? If I wanted to find the area of some weird, awkward, curvy-shaped region, then yeah, I pretty much integrated, yeah? What I did was I split it up into rectangles, and then I found the area of all those rectangles and added them all up. All right, a little subtle sort of and weird philosophical thing happened in the course of doing this. While solving the area problem, I also just decided that the very concept of area was best defined via this process. And so while I started, well, can you sit down now without falling asleep? Okay, good. Stay standing then. All right. So while our goal was to find the area under the curve, somewhere during this process we decided let's just define area under a curve to be whatever you get when you draw n rectangles and then let the number of rectangles go to infinity. Okay, so volume has like a whole nother long and complicated weird history to it. And if we wanted to, remember on the first day of class where I sort of set the tone by like posing the area problem, and Kelly, we did this whole thing where we're like, we can find the area of a square, we can find the area of a rectangle, triangle, trapezoid, etc. And then polygons, and then it got hard when we did circles, we had to do fake calculus. We can do the same thing with volume. What is the most basic possible volume shape? Cube. And then, oh, it's as if that there was some volume video made by a brilliant math teacher on the internet, which was assigned to you a month ago. There was, yeah, it's me. In which I, over the course of 25 minutes, produced a nice series all about how you take a cube, you can then use that to find the area of a box. Once you can find the area of the box, you can find the area of a cylinder by letting the base letting the number of sides of the base go to infinity. You can find the area of a pyramid by decomposing like a box into different shapes. And then once you can do pyramids, you can do cones, and the one that's really hard is sphere. Okay. But what we would like to do now is not just stop at the basic shapes from antiquity, like sphere and pyramid and cone. We'd like to just find the volume of anything. Crazy, weird, irregularly shaped figures. And how are we going to do this? Well, first we have to recognize how little we really understand the concept of volume. And the way I copied this, I passed out this thing which I copied from like a textbook, and it says, okay, the most basic concept of volume is the volume of a cylinder. Although they define cylinder kind of strangely. The way we talk about cylinder in like high school geometry is it's like there's like a it's like a circle and then like whatever, and then there's like a height. Claim the area, I think I might have done this in the video also, the area of the volume of this thing is just the area of the circle times the height. But we could also, the way this thing does it, they also define, they also are going to call this a cylinder. Something went wrong there. In this case, also, the volume of that cylinder is going to be the area of the base times the height. But we could also have, like you see before you, this like packet, we could also have a quote-unquote cylinder in which the bases are like parabolic regions. So assuming that we've solved the area problem, I would like to again assert that the volume of this quote-unquote cylinder is just the area of the parabolic region times the height. Yes, later.
Can I have a packet?
Yeah. Come go. Brittany, we are now going to find the volume of some irregularly shaped thing. So, okay, here comes this weird drawing. I think I was supposed to do this first and then pass out the packet, but I forgot. So you have it in front of you, because I'm not such a good artist, but I will try my best. So imagine that I'm trying to find the volume of some weird three-dimensional object, which kind of looks like a big, like sort of like weird, like, well, maybe like, I don't know, I'll draw it. It looks kind of like this, and then over here it looks kind of like this, and then it kind of gets bigger, and then like smaller again. So it looks like some sort of like sea squirt, or like weird, just like kind of like weird, like fish or something, like a mean. No, how do I draw? Well, I guess the eyes would be like over here. No, I guess it would be like. Yeah, that's like an eye. Yeah, yeah, and then maybe like a smile. No, I'm kind of confused about what's going on here. Goal, let's find the volume of this weird object. Well, this is brilliant, because I have this thing called integration. And what integration really does, integration says that if I want to find something, and that process involves splitting that thing up into an infinite number of infinitely small things and adding them all up, then this is a problem which I can solve via integration. And so that's exactly what I'm going to do here. I'm going to take this weird blobby fish thing, and I am going to align the axis of the fish along the interval from A to B. And then I am going to slice this fish up into many tiny fish pieces. So, chop. And we're going to get like sushi basically, right? And these little pieces of like, these little sort of like slices of like fish bread or whatever. So does everyone see what's going on here? My picture's not terrible, it's pretty good actually. So we cut, and we slice them up. Well, can I figure out what the volume of one slice is? Griffin, yeah, I can do this, watch. This is the kind of part that's a little bit hard to draw, which is why the picture is like sort of helpful. So here I pick an arbitrary point x on the x-axis, and I slice a plane through the fish. And when I slice through the fish with some kind of plane, I'm going to get, man, my art skills are kind of bad, so if you're really good at drawing, I'm just sorry, you're going to have to just cringe in horror as I just like...
Honestly, it looks pretty nice.
It looks okay, right? Yeah, thanks. All right, so, yeah, it could be better. So a cross-section of the fish is going to look like, well, a cross-section of the fish. It's going to look like a tuna steak, basically. And in fact, it kind of looks like, can you collect me some of those like erasers? Yeah, they don't throw very well though. Okay, one more, please. It kind of looks like a cross-section tuna steak thing is kind of going to look like a little bit like this, right? And so what we're really doing is we're decomposing this fish into a bunch of tuna steaks, yeah? Okay, and if I can find the area of one of these cross sections, then I can multiply kind of like by the thickness, right? So Brittany, let's suppose that I have a function a of x, which gives me the area. So this is the area of a cross section. This is the area of a cross section. Then now what I'm going to do is I'm going to make it just like a little bit sort of thicker or whatever. Now the picture's getting bad. But you guys kind of see what I'm doing? I'm giving it a thickness, and the thickness is just like dx. And so if I want to find the volume of this fish, what I'm really going to do is I'm going to take the sum from I equals 1 to n. I'm going to take this interval, I'm going to partition this interval up into subintervals, I'm going to go over to the ith interval, I'm going to pick a sample point on the ith interval, and then I'm going to plug that sample point into my function, which tells me what the area for a given x value of the cross-sectional fish thing is, and then I'm going to multiply by delta x, which is the width of that interval. And then by my axiom about volume, the volume of any object is just, of any cylinder, is just the area of the base times the height. And if I add all these up, then that's the entire volume of the fish. Except not exactly, because it's not exactly true, like the fish's shape changes a little bit, even over small intervals, so what do I need to do? I need to take the limit as n goes to infinity. And this is, of course, a Riemann sum, and thus I can solve this with an integral, because it's an integral from a to b of a of x dx. Okay, so really the last thing we're going to do in this class, today and also next week, is to use this general process to find the volumes of things. And anything I would like to find the volume of is going to proceed along this basic design, which is split it up into an infinite number of infinitely small pieces and add them all up, and integration will do that for us. Okay, sound good? Okay. So though all these volume problems are sort of the same, it is typical to sort of teach them in 3 different sections, kind of. So what we're going to do today is what's called volume well, we're going to call it volume by discs and washers. And what we're going to look at first is the volume of so-called how are they called? Objects of rotation. That's not what they're called though. I'll think of it in a second. Anyway, let's just do one. Next page, page 3. We're going to do all these problems right now. What do we got left? Like a half an hour? I wish. 25 minutes? Okay, good. 25 minutes. We'll go fast. Number 1. Find the volume. We're on page 3. Psst, we're on page 3. Let's go fast. Find the volume of the solid formed by rotating about the x-axis the region bounded by y equals x squared, y equals 0, and x equals 2. Okay, please read that like 3 more times, and then draw a nice big picture of what is actually going on. Yep. Okay, wait, Nikili, food away. Math only, no talking. Silence, focused effort. From now to the end of the period. Really important is to draw a very large, neat, high quality diagram of first the region which is being rotated. Okay, so I'm rotating some region. Please, like I said, please first just draw the region which is being rotated. And according to this, the region under discussion is the region between y equals x squared, y equals 0, and x equals 2. Does everyone have the same region I have? I really feel like it's a good, the first step should be just draw the region. Okay, so there's my region. What am I doing with this region? Rotating it about which axis? The x-axis. So now draw in a little rotation symbol to indicate and to remind you that we are rotating. Come on, man. Large, neat, high-quality diagrams. Bigger, neater, more high-quality, labeled, all that kind of stuff. Shade your region, draw your rotation symbol, and now take a minute and just like imagine what happens when this is rotated. Yes?
I have a question. So,
Yep.
it's bounded by x equals 2, right? So why doesn't it go like that way?
Because it's the region enclosed by y equals 0, x equals 2, and y equals x squared.
Oh.
I mean, I could